given 4 indicators, and then white height is represent dimension as the bus. So return string represent the category of the bus. If any dimension of the box is greater than this value, box is greater than this. And okay, so just do this case. So any dimension is greater than this dimension, so greater than equal to this. Just do as part of saying. Okay. And values. Okay. So it's the first case, and the maze of greater than equal is heavy. So heavy is heavy. And if the box bulky and heavy, schedule is both also. Neither okay, suppose neither, else written as bulky or heavy. Bulky or heavy. So in this case, heavy and neither. Okay. Case by case. So problem 2, find consecutive indicators from a data string. So for a string of indicators, implement the structure to check the last k indicators passed in the string equal to the value. What it means? So we can check the last k indicators equal to value. So basically, initialize object with the value of k. So it's 4 and k. Alright, so we need to check the string is equal to 4. So consec is add number. Okay. So if less than equal condition is not hold, alright, so that's idea. It's that we can use the value also we need a count and the value k Now we see total k. Let's say count at 1. Count is greater than k value. Otherwise, say count is equal to 0. It's right here. Okay, so false, false, true, false. That's a consecutive. And about problem 3, you given the 0 index and numbers, and the effective value of this 3 index is defined as the or after or end, and you want to find the cruciability of the array. It's cruciability is the crucial of the or possible triples. So Gore find cruciability and effective, it's equal to ijk is like this, so it's or value and the end value. Okay, so think it will be okay, you want to find cruciability, so let's consider this example. ijk have no, we can do any 3 values, and then we can change the order of this. So 1 can be here, and this can be 1, 1, 0. Alright, so it's something like something like what? I need to think it. Okay, so in the first case, you see example 1. Do you have any idea? No. Maybe I need to see some example. So 1, 4. We have some such many pairs 8. And you can see that it's at 1. We have 3, 1. We have 3, 1, and we also have 3, 4. And we also have okay, so also have 0. Okay, so it's 1 and 4. It's 1 and 4, and okay. So well, it's something need to consider. Maybe you need to think what is OR. So consider 1 digit of this. You may know that it's consider each digit of this. Consider each digit of this, because we can separate it. Separate the digit, the bits. We can separate bits because each bit we can see as independent. So 1 and 4 we see as 0, 1, 1, 0. It's like this. This is the first example, and consider we can have each position have 2. I have 2 possible, J has 2 possible, K has 2 possible, so it's 8. And you need to think in that it's the first bit of this is 1, 0, so it's like so it's a 1, 1, 0, and so or an end, so to 0. We may get it's okay. If all 1, consider the last digit. If all 1, and okay, if all 1, let's say it's think about this kind of information of this? So consider this digit. If this digit is 0, we need to calculate the accuracy of this, right? So what is the number if this bit is 1? So we need to do or value should be 1, or value should be 0, and it should be 1. So this kind of case, kind of bits will be 1, and what kind of pattern of this? Because the end means that this bits always be 1 if we need 1. So calculate the number of 1 bit is 1. Is set or is set. Say the ijk, the k should always be 1, because if this is not 1, if this is 0, the value is 0, so we only carry number of the bit which is set. We only carries this. That will inverse our answers, right? So only contribute to our answer is we only consider numbers of 1 of this. Okay, so I have some idea. Each bit. Okay, so each bit we can separate a bit. This is main information of this, and okay, so consider that you only need to think is numbers of 1. How many numbers of 1 of this? We need to think is, so k, we have 2 1, right? So we have 2 1. We have number of 1. It's only 1 possible, and okay, so this we can be 1 1, or we can be 1 0 1. We can be 1 0. We only need to think this pattern. So calculate this pattern. We will get an answer. This is all 1. Okay, I may have some idea. So now let's say for each bit, alright, so say 1 0. So count this 0 1. So for x numbers, and we want to consider is that the answer. Okay, count x I and 1. If this is odd, yeah, this is odd. Or we're saying that if x, or say, yeah, this is 0 and 1. Okay, and now we consider this pattern of this. So first case is total number. First pattern is 1. This is 1 and this both is 1. So it's first case is count 1, count 1, count 1. Okay, use this, and the second case is that 0, 1, 0. If total count number is odd, answers will over this bit. Let me be the answer. Okay. Right, this may be long. Careful. Right, that's the idea. Okay. So about problem 4. The maximum and minimum of per city. Okay, so this kind of problems. It's what? It's stations of length n. Stations either represent the numbers of power stations in ICT. Each power station can provide a fixed range. What it means? Okay, we can provide a city a fixed range. In other words, it's a range known as R, and the power of a city can provide it, or a city's J, such that this distance. Okay, so distance is can provide the power if the range is 1, and so it's a power. Okay, and okay, absolute value. So 752, 3. Okay, the power of the city is total numbers of the power stations being provided power for. The government have a section. What is it? Building K-Moore's power stations, each of which can build in any cities and have some range as pre-exists one. Maximum possible minimum power of a city. Maximum possible mini power. Additional power station are built optimally. You can build K power station in multiple cities. Alright, I don't understand the problem. Okay, let's just look at it again. So what it means, what is a K? The power station can provide power to every city. This is the power station. Also, we can provide to every cities. Okay, cities is between the each cities have a power station, right? So power is the total numbers of power stations is being provided. Oh, okay. So the power of C0 is we can provide by 1, right? So it's 1, 2, 4. Okay. And also we have some sections building the K-Moore power stations. Each can build in any city and have some range as pre-exists 1. What is the K? Okay, K. I don't understand. Let's see the explanation. If we install the power station at C1, this, so it's 14450. Can each building any cities ranges species 1? Okay. I know that. So if we can add, so K can add any stations of this. Okay. K can add any stations. And idea, we must add So we may get it 6. So, wow. Some kind of problem you need to think. Stations. It's what? Oh, I missed something. Alright, so what? If I want to increase into 6, okay, maybe you can guess. Oh, alright, so binary search. Such a good idea, right? Very easy to implement and maybe bug-free for this problem. So let's say if we know that the minimum is 5, right? We know the minimum is 5. How do we get it? We can say and this is fixed. And now given the 5, we say the pattern of this is we want to get is 5. So we will try to do what? We'll try to do it's increasing the range of this before range add. So the problem is that how to range add something. This is tree. We don't add a single. We may add it to the middle point of this. If this is 2, we may add this pattern of this. Okay. So. Okay, cool. Oh, alright. Nice sweep, right? This is a good idea. This binary search. 0 hours 13, 5, and also can I guess the answer? Let's say the minimum it's plus by 2. If good, let's say we want to guess the maximum of the minimum, right? So answer is mean, and it was mean plus 1. So it was mean minus 1. And also say the mean. How do we check? Good. It's in this kind of information of this, we need to calculate the power of each, and we check the operation. It's smaller than k. Let's say this is satisfied, right? This is satisfied. Alright, so alright, spider search and let's sweep. Okay, consider this case. In this case, we know it's 1, right? So 1 means that we will add current position at remain at I, and we will add I plus 2 minus remain. That's its idea. So consider this. If this is 1, we say this will be add, this will be add, this will be add, and this will not add. Okay. Cool. Okay. So we use nice sweep. Oh, the add operation. Stations. Okay. So we need to consider the initial of the power of only of this. So let's say stations is that it's the stations sliding window of this. So it's sliding window with 2. Or sliding window 1. Sliding window 1 if distance 0. Window size it's R plus 1. Okay, and can do it twice. To make the problem easier, and power 0. So power we are do this again. Do the operation of this sliding window. Sliding window. Okay. I think this can be done with 2 paths, right? So we reverse it and build it again. Yeah, that's the idea. Alright, so we add stations I and have a window plus if window say I is greater than 1, say power. I will add a sum minus I minus R stations. If this is 1, we will minus 0 this. Okay. Yeah, we just do it again. And we will duplicate. Let's see the part of this. Let's see this. Okay, range. Let's see this. Yeah, it's the base case, right? It's a base. Yeah, it's good. The base is good. It's fixed. And yeah, reverse it again. This is suffix. And we reverse. So you can use that as a prefix approach. Yeah, and okay, so for I, can use more. Alright, so just do me. Okay, so temp is polar. If temp is smaller than mid, rolling sum, rolling 0, rolling will add, and if the temp is smaller, then we still need add. So the cause of this will be the cause of this will be the alright, so the operations will add a need and the add so it's a rolling. Add the need and current position add 2, add 1 minus the need. Early start. Yes, good. So by the search of this. Right, so nice sweep and binary search. Interesting problem. Okay. Cool. Still waste a lot of time for this. Yeah, but actually I think I may do better. Still waste some time to figure out if this is a binary search problem, but I just need to. Yeah, I can do better because I can do better actually. Yeah, I can do better actually. It's problem statement reading so long and yeah, okay. Alright, that's good. Okay, so I'll answer make sure that it's in the bound. Okay. Need to actually start. Cool. Alright. So okay. And see. You can see problem 1 to 4. Let's see this problem. So for this problem, I think it's at problem 1, and you need to categorize the bus according to the criteria, and it's actually nothing I need to talk about this problem because you just do as a problem saying the value it's the product of the length and width, width and height, and right. So just do as the problem saying. If a bulky, we can use the boolean to check that is a bulky or is a mass is a heavy. So if they have both bulky and heavy, they are both. Otherwise, neither of this is bulky nor heavy. It's neither. Otherwise, is check if it's bulky, return bulky. If it's heavy, return heavy. So just do as problem saying. Yeah. So first you check that the condition of each dimension is greater than this, and the value is greater than this 10 power of 9. Mass is greater than 100. And problem 2. Just design a data structure such that we can calculate the consecutive integers less k integers equal to k is equal to value. So basically we can do is that we need to know the continuous, and we also need to know the value. And when we add value, if it is equal to value, we calculate the counter. Otherwise, we reset the counter. So we can use the counter to do that. If equal to value, let's add the counter. Otherwise, reset the counter and return that if the counter is greater than k, that means that's consecutive number is value. last k consecutive integers value. So yeah, let's just return it. Let's problem 2. The bottom problem 3 is saying gets equals 0. You want to know the all of this and consider this. IJK doesn't have any condition. And let's see that each bit separated. Do each bit separated. So we only need to consider is the 1 because the equals 0 or only care about the equals 0 is 1. The 0 cannot change the equals 0 value. So we need to care is equals 0, 1, and we need to calculate how many number of equals 0. How many number of equals 0 is 1, right? So yeah. Okay. So in this sync. Okay, so see this condition. Equals 0 is 1. Is that then this must be 1 and this or this is at least 1, right? So we have 3 pattern, this pattern, this pattern, and this pattern. We just calculate this separately. So first thing, we just calculate the 0 and the 1 number of lists. After that, we just calculate, okay, so total number of lists is auto event because the equals 0, or you know that the equals 0 of all lists is that 1 and 1 equals 0 is equal to 0. So the old may contribute the equals 0 value. So if this is odd, we just contribute the value of this. Yeah, let's write there and think this is a problem 3. So separate a bit, calculate 0, 1 numbers and product it. Yeah, this may be overflow, but yeah, but I don't know. Let's accept. So yeah, let's see. Okay. It's yeah, interesting, but this can be overflow, but so I just yeah, just sum it again. Okay, sum it again because yeah, no, it's maybe overflow. So with this can be rejudged. Right, so if odd, we contribute to answers of this bit, right? Separate a bit because we don't. Each bit is independent. Okay, so this is problem 3. So about problem 4, you want to maximize and minimize the power cities, right? And also need to you need to the problem statement is that we have a power we have stations of a length and we have n cities, and what is the power of city is that is the total number of a power station. So power station is what? Power station is this array. And each power station can provide power to every city in the fixed range. The left and right, the range is R. We can provide the power to that city. So consider this case if the city final is like this, then the power of city 0 can, because the range is 1, so this can distribute to the left, this can distribute to the right. So city 0 is 1 and 4, city 1 is this, 144, 445, 450, 50. So it's like this. Okay. And what? Okay. And what? And you also have a K. You can add K. You can add K to some power station. So in this example, we add 2. So get 144. You can increase in the value. right? So we want to find the minimum. We want to maximize the minimum of list. In this example, the minimum of list is 5. So we want to maximum. And what is idea? Okay. So think about this. So first important is that we can pre-calculate the station. We can pre-calculate the power of the original, of the initial power, the initial power of each city. So in this example, in the example 1, the initial power is this. And how do we calculate it? We can use the sliding window approach to calculate this. Suffix, prefix, and minus the duplicate one, because self is duplicate, self is duplicate, self is duplicate. So we minus this. And yeah, to calculate the power, we suffix is simple. We just reverse and do it again. And yeah, the formula is almost the same thing. And this can use as a function, I think, to make coding better. And after that, we subtract the self, because this is duplicate calculated. And what is the main idea is that, okay, think about this minimum. Consider that if you give you the minimum of the station of this, we say we want to get minimize 5. We know this minimize 5 is easy to implement it because if you know the minimize 5, we just add this 2. But we don't want to add this station. We may add the middle station, right? So actually, this range will be changed, will be updated, will be modified. So we can calculate the formula. We can add the left point and add what? The R and R. So it's the twice. It's the 2 times of R. So this range will add 2. This range will add 2. 2, 2, 2. Right? So that's why I add this and what? But an important technology is that you cannot just for loop to add 2 of this, because it's too slow. So we need to use a line sweep. We only add the left position and use a rowing. We only add 2. This don't add. We just when we add 2, we just use the previous value. So this is 2, and this value is 0, and this minus 2. So this will get 2, and in this becomes 0. So the rowing in this index is 0. We don't, and in this will be 2 to 2. So it's very good. So we just use the line sweep approach. Now let's the operation. We need to check that when we are adding 2, we need to check that the operation is more than k. So that means that we can get this kind of power, right? So let's see this. So if given the minimum, you want to find operation is smaller than k. So we just do from left to right when we are adding the rowing song. When we are trying to add what is the current power of this, and if this is too small, that means that we need add. After we add, operation updated, and the left position will be minus 2. So consider this. With this, we need 2. This position need 2, so this will be minus 2. What is this? 0 adds 2 times R, add 1 is 3. So minus 2. Yeah. That's it. And I already stopped it. And just minor search. the best answer of this, because why I can Binary search, because it's very straightforward. Because streak can work, that means that 2 also can work. 1 also can work. So we have this is the monotonic, you know. Okay, so binary search it. Alright, so that's the problem 4. Alright. Let's see the friend ranking. Okay, good.